Good afternoon with everyone. I have the pleasure to talk about the dynamic Griffiths phase, a mechanism for emergence of conscious state. This is my group of investigation. This group of investigation came from Yachaytac in Ecuador. Okay, so have you ever think why the nature has so many stable states? For example, the matter. There are liquid, solid, and gas. What is in the middle of each stable state? Can any dynamical system live in this middle? From a long time, from physical statistics, they asked these kind of questions, and they found that in order to cross state 1 to state 2, you should pass to a critical point. But in 1969, Griffiths found a mechanism to pass from a critical point into a critical region, as you can see in the figure. Perfect. From dynamical systems in 2016, Kunihiko Kaneko proposed this equation in which you will obtain critical regions that will have a name as Griffiths phase. This dynamical equation has random connections, and the local dynamics of each node of each element will be a logistic map. So as you can see, he found the mechanism to obtain Griffiths phase. This first mechanism will be the random topology, because the way in which each node are connected will be as an Erdos rangy network. Perfect. What is the Griffiths phase? As you can see, there are 3 phases in this system. The both stable phases are the desynchronization phase, as you can see in the left, and also the synchronization phase, as you can see in the right. Dynamical Griffiths phase are able to coexist between both and generates spontaneously each phase of the system. The long clusters are desynchronization, and the really short clusters with only one color are synchronization state. Perfect. So we try to keep this mechanism, but we don't obtain the perfect Griffiths phase from dynamical of the brain. So we should consider some important things from brain dynamics in order to obtain this. So in 2010, there is a beautiful paper from Dante Chalbo, which calls Emergence of Complex Neural Dynamics. This paper gives us beautiful ideas of how to model the brain. So one of these, the main idea, is the fact that neurons are non-linear elements. This is clearly, there are no linear, they have a peak. The another important thing is to know that the interaction between the brain and the environment exhibits a scale invariance. This will be crucial for the future results. And also, the first time that they find this idea, that they give this idea, is in 1941. There is a beautiful video that explains this in internet. It's a critical point explanation from John Beck. And another idea that should maintain in our brain is the balance between the segregation of ideas and the integration of memories. This is crucial for how our brain should maintain the optimal function. Okay, so we keep this in mind. We have how the brain, how a neuron works individually, as you can see in the plot, and we put these Chalbo dynamic equations inside the Kaneko coupled map with random topology, and we only obtain 2 phases. We don't get a Griffiths phase in this system. So the main idea to improve our model to the real world are by the hand of a book of MIT that calls Networks of the Brain from Olaf Sporns. He said that environments with a high level of heterogeneity implies that systems that lives in this environment must demonstrate a diverse range of response, also a heterogeneity kind of response. This can be clearly if we ask a question to any of our partners from where they come or what is your name, for example, and the person will answer differently according his name. This is the same. The perturbation is different. The response to the perturbation will be different from different neurons. So not all the neurons are equal. From this kind of thing will be called the law of required variety. So the idea is that in our Chalbo neuron equations, we will change the parameter of response randomly, and the responses will be considered as an heterogeneity. This kind of thing, as you can see in the illustration, is fundamental to obtain some answers. In our case, we obtain the Griffiths phase inside the brain. But as you know, in physicists, when you work with systems with invariant of scale, you cannot use usual measures such as the mean field or this kind of measures, because these don't detect the impartial distributions. So in our case, we develop one measure. This measure will be called the dispersion of fraction of clusters, as you can see in the plot below. And with this measure, we can find the peak will detect the Griffiths phase. So let's see how it works. We can see three regions. The first region is the desynchronization phase, as you can see in the time series. The third region is the synchronization phase, as you can see in the right plot. But in the middle of the plot, which usually is a point of transition with the mechanism of heterogeneity, we develop a region of criticality. And the measure picks up in this region, as you can see. Perfect. So from this, we can say, we have the pleasure to say that we found a new mechanism that has been reported in some places as the heterogeneity response, which will be the mechanism 2. In order to consider this as an enough mechanism, we should change the topology in order to see how will be the Griffiths phase, which will be the difference. So we do the same with different kind of local dynamics inside the Kaneko equations. We do the same with logarithmic, we do the same with quadratic and with Chalbo equations, and also in all we found the Griffiths phase, which is a range of parameters. So one important thing that to consider this critical region as a critical region is the scale invariance. So we prove it from our model, consider 16,000 of neurons over 100 of steps, and meaning 40 different networks with different initial conditions. As you can see, it follows the scale invariance. It follows a power law that changes with the epsilon. This is consistent with experimental evidence done by John Beck from a paper of 2003. And this is a wonderful result that verifies our model. The conclusion that we want to give is that in 2021, in December, Daniel Tucker writes a wonderful perspective paper in which he said that the consciousness is supported by near critical slow cortical electrodynamic. He proposed from literature and also from experiments the idea that the waking conscious states are in a critical point. And when you are not in a critical point, the information behind this conscious state will be considered as how much information you can procedure or you can learn or listen or speaking. When you are unconscious, you cannot develop this information. So this information will peak when you are conscious and it will be down when you are unconscious. And it's interestingly that our results from our measure are consistent with all this area of information behind conscious activity. As a summary, we develop, first, we proved the mechanism of random topology. Second, we found a new mechanism, which will be the heterogeneity response. Also, we say that obviously there are a third mechanism, which is a combination of both. We develop a unique measure that detects this. And also we prove the scaling variance that verifies the criticality inside the brain. But the most beautiful result is a question, because from different mechanisms, we obtain the same result. So this developed as a question that is there any relationship between spatial heterogeneity and random topology? Okay, thank you a lot.